In tabletop rearrangement and planning, we arrange the given objects on a table to a specified final configuration. It is challenging due to the variations and the type of objects one can encounter in the scene and the variations in the kind of tasks one has to solve. These tasks can range from a direct pick and place to decluttering the scene before picking or placing objects in tight spaces where an arm has limited maneuverability. IIIT team had provided us with a baseline to solve a typical rearrangement planning problem. We have improvised on this baseline by solving specific rearrangement planning challenges. The baseline was not able to handle such scenarios where multiple instances of an object existed. Instead of using an instance-based segmentation approach, we handled it by adding markers to detected objects during feature matching. The feature detectors used by us look for textures while detecting an object. By masking these objects, we essentially remove the textures. So, the same object won't be assigned a new pose again. Usually, instance segmentation approaches are used to predict grasp poses on individual objects. In our situations, we wanted to consider the surrounding objects as we would avoid grasps that could lead to collisions. For example, in this current scene, in order to produce collision-free grasp points for the plier, it should choose a grasp pose that does not lead to a collision with the screwdriver or other nearby objects. Therefore, it is essential to send the entire point cloud. However, sending this entire scene point cloud to 6DoF GraspNet without instance segmentation produces sparse grasps. In order to generate denser grasps on the entire scene point cloud, we chose Contact GraspNet by Sundermeyer and team. This drastically improved the average number of objects successfully picked per scene. The grasp poses were being predicted for the entire scene point cloud. We then had to filter and assign suitable grasp poses to each object. We used a bounding box-based approach to prevent the assignment of grasp poses belonging to other nearby objects in the clutter. For each object, we fit a bounding box and assigned the grasp poses that fall inside this bounding box to that particular object. The monotone instances are those instances where all the objects are moved at most once to reach the final scene configuration. Non-monotone instances are where at least one object is placed in some intermediate position before moving it again to its final configuration. For example, suppose some other objects partially or wholly occupy the goal position of the current picked object. In that case, the robot must place the object in the intermediate position until the clutter at its goal pose is cleared out. We have seen a good number of non-monotonic instances in this competition, so we came up with a planner that considers such instances. Another big challenge in such instances is differentiating the stack placement from the unnecessary clutter. Sometimes, the goal position may be occupied by some object that is supposed to be placed under the current object in the final state. Detecting whether that's the case is important before choosing to go for intermediate positions for placement. We have solved these problems posed by non-monotonic scenes with a new heuristic-based task planner developed for this competition. Unlike the PDD stream-based task planner used by the baseline, which generates the whole plan at once, our planner is dynamic and can pick the next best object choice based on the current state of the environment. We first use the object's goal poses to detect stacking in the final configuration of the scenes and divide all the objects into a set of stacks. Some stacks can have only one object. While looking for the next best object, the planer first looks for the objects whose goal states free and are the bottom objects of their corresponding stacks in the final configuration. If such an object is detected, it will be simply placed in its target. If the object's goal state is occupied, it may be occupied by other objects belonging to the same stack or due to some random clutter. We check if all the objects that are to be placed under the current object in the stack are placed in their positions or not, using a simple memory array. If they are already placed, then we simply place the current object in its target position, without worrying about the occupancy of its goal state. If all the objects that are supposed to be placed under the current object are not placed already, we then place the current object in a buffer state. To minimize the error, we sample a buffer state that is closest to the target configuration and is free of collision at the same time with the help of a fast convolution-based algorithm that represents the object as a kernel and convolves over a 2D occupancy map for collisions. This way, we tried to handle the non-monotonic instances in this competition. Initially, with the baseline approach, we observed some erratic behavior while planning in the Cartesian space. It has been commonly observed in many manipulator demonstrations that a specific rest pose has been used during rearrangement planning tasks. Similarly, we defined a rest pose that the robot will move to after each pick or place operation. We started working on the end-to-end rearrangement planning topic with this competition. In the last few months, we realized that we are still far from solving an end-to-end autonomous rearrangement planning completely. This opened up a lot of new potential research problems. We are looking forward to solving many of them in the near future. Thanks to the organizers for this wonderful opportunity to participate in and learn from the competition.